Hey YouTube! So last time we looked at the derivative as a means of approximating function values using some sort of a tangent line. Okay, so we talked about the equation of a tangent line and how to manipulate that and use linear approximation. And one of the applications that I mentioned was something called a differential. Okay, so suppose that I have some expression dy, or a differential change in y, is equal to the derivative or slope at a point x times the change in x. Okay, so earlier I said that this expression was meaningless technically because both dy and dx are going to zero at different rates, and you really aren't going to get anything out of it unless you compare them. So I'm going to do something right now that you probably shouldn't take with too much veracity, because I'm going to have people all over trying to manipulate this in weird ways. So just keep that in mind. If I take this expression and divide it by dx, okay, then what I'm going to get is that dy dx, which is the derivative as we know it, is equal to f prime of x. In other words, if I compare this, if I divide both sides by dx, this infinitesimal rate, these are going to zero at different rates, and when you compare them, you get a slope value, an instantaneous slope value, which is known as the derivative. Okay, but I want to talk about what dy dx actually means in terms of rates of change, because that's commonly what we see derivatives being used for in the real world. Okay, so what dy dx actually represents, well, this y, how you would say this, is I am taking the derivative of y, so let me go ahead and write that. So I'm taking the derivative of y, right, with respect to x, or whatever variable's on here. This could be dn dt or dm d alpha. It doesn't really matter, but I'm taking the derivative of this variable with respect to that variable. Right? So that's a very important thing to keep saying to yourself over and over and muttering as you're doing these types of problems. Okay, so suppose that I have some sort of a picture of a function. It's doing that guy. And I want to find the derivative at that point. Well, you understand that I can use a tangent line, use this idea of the tangent line, to linearly approximate values that are in the range, in the neighborhood of the point of tangency. But what this actually represents, dy dx, well, dy dx is the instantaneous rate of change of a function y. Okay, so dy dx talks about a rate of change, and here's how. You might have noticed that as slope changes, as it increases, your function is increasing at a faster rate per unit of x, right? Now, on the coordinate axis, we're just gonna talk about every single marker as a unit of x, a horizontal distance of 1. It doesn't really matter what that 1 represents. It could be centimeters, it could be furlongs, it doesn't matter. But if I go one horizontal distance on the x-axis, how is my function changing at that point in time? So this slope, for instance, looks to be a little less than 1. So I have to travel more on the x-axis for a smaller change on the y-axis. Okay, but it looks like my slope increases as I move along this function to where 1 unit of x gives me a larger change in y. So if I have a slope and I tell you the slope is, say, 5, for instance, then you commonly say, well, if my slope, or my f prime of x, equals 5, you connect it with this dy dx idea, and you take 5 and say, well, I know this is 5 over 1. I know that I'm changing at a rate of 5 on the y-axis for every 1 on the x-axis. If I give you a slope of 1/4, you can either say, well, I'm going up by 1/4 on the y-axis for every 1 on the x-axis, or I'm going 1 on the y-axis for every 4 on the x-axis. Either way, x is increasing faster. You're traveling more along that axis than the y-axis. So your function isn't doing a whole lot of change as far as on the vertical scale, which is what dy dx represents as slope. So I want to talk about an application really quickly that I think is overused a lot, but it's still important to at least bring up. And that's the idea of velocity, position, and acceleration in one-dimensional kinematics. So suppose that I have a function and we'll say that for a given time, it's a function of time. I could plug in any time value and get the position at that instant of, say, a particle or a moving object or an inanimate object like a baseball that's being thrown. Okay, so I have this function x of t. That function gives me a position of an object with a time. So for a given value of time. Okay, so let's kind of connect this to what we understand about position and Newtonian mechanics. Okay, so if I have this position function right here, it gives me the position of an object given any time that I'd like. Well, what if I wanted to measure the rate of change, how fast my position is changing relative to time? So if 1 second passes, how fast is my position changing? So think about traveling in a car, and I don't know, you're passing a lot of football fields, and you're traveling on, I don't know, 1 football field a second. That's a really fast car, but 1 football field a second. If you're consistently passing 1 football field a second, you're changing your position at a constant rate. So if I wanted to take the derivative with respect to time and measure how quickly my position is changing, you're going to get just a number. Okay, maybe 1 as your derivative, 1 football field per second. So if I take the derivative of this position function, what you're technically doing is you're taking the limit as delta t approaches 0 of delta x over delta t. So you might recognize this quantity from a remedial physics class. How fast is my position changing relative to time? And you might know that to be speed or velocity. Okay, so this idea of velocity, this is actually average velocity because it takes 2 distinguished points, 2 distinguishable positions, and it compares how long it took to go from point A to point B. So if I throw a baseball from point A to point B with a distance of, say, 3 meters, if I threw that baseball 3 meters in 2 seconds, my velocity is 3 over 2, or 1.5 meters per second. So if you've seen units like meters per second or kilometers per hour, you know that it's a measure of velocity. So therefore, if I look at the instantaneous rate, if I want to know the exact change at a given point in time, the derivative with respect to t of this position function is actually just the velocity function. We'll call that v of t. All right, and this is really just the first derivative x prime of t. Okay, the derivative of my position function is velocity. Right, so just to emphasize that, if you didn't know, velocity is really distance. This is technically displacement because it's a vector, but we're not going to worry about that. It's distance over time. And again, if you don't believe me, just think back to those units of velocity or speed, meters per second, kilometers per hour. Right? All right, likewise, I can do the same thing with the velocity function. I can take this velocity function and differentiate that and look at how fast my velocity is changing relative to time. Okay. So say I pass 1 football field per second, and then I suddenly pass 2.5 football fields per second. Okay? Before calling the police because you're going out of control, okay, you realize that you're changing the rate of position. The rate of change of your position is actually increasing. You're displacing more field, more road per unit of time as time progresses. So the derivative of your velocity is changing. Okay, so this would be the limit as delta t approaches 0 of delta v over delta t. So in this case, you might know delta V over delta T to be acceleration. Okay, so this is acceleration. And acceleration is just velocity over time. So gravity is a common acceleration. It's meters per second squared, or meters per second, right? So this is really acceleration. And in Newtonian mechanics, we make one fundamental assumption. We say that acceleration in and of itself doesn't change. Right? Because if acceleration changed, that's a really hard concept to wrap your mind around. So in general, I'm going to go ahead and say that we're not going to be working with anything beyond the second derivative. And you're probably not going to see anything like that anyway. I'm convinced myself that our minds just aren't intelligent enough to understand anything beyond the second derivative. That's why most equations deal only with the first and second derivative. There's a fourth derivative. I believe it's called the biharmonic equation, but you'll never probably see that, so don't worry about it. So this is the first derivative of velocity. You're looking at how velocity changes with respect to time, and this is also the same as taking your position function, differentiating once, differentiating twice. This is really the second derivative denoted with 2 ticks, right? So again, I feel like this is overemphasized in classes, but I thought I would go over it so I don't have to do it again. Okay. I want to look at a really interesting rate of change in the business world, and that's the concept of revenue. So before you tune out, I understand business isn't everyone's favorite, but this is actually really cool, and I think it's intuitive. So just hang with me a little bit. So what I want to know, essentially, I want to know how revenue changes with increases in price. So if I change the price of a good that I'm selling, how does that affect my revenue? Okay, so say that Apple was selling their iPhones for like what, 200? No, they do sell them for 200, like $2,000. Okay, are you going to buy more of them? God, I hope not. But if they sold them for like 5 cents, you would think more people would buy them, but more people might assume that there is some defect in the Apple product causing them to lower the price so much. So it just depends. We're going to look at how revenue is affected. So when I say revenue, by the way, I'm only defining the money that you take home from your good or service. I'm not talking about the cost of making or producing that good. So how is revenue affected by changes in price? So we're going to differentiate and see how cool this is. All right, so in general, if I want to talk about revenue, revenue depends on really 2 things. Okay, so imagine you're a business owner or an entrepreneur, and you just made a good and you want to sell that. How much money do you take home? Well, that depends on 2 things. So the revenue earned depends on how much it costs, so the price of the item, and how many items you sell. Okay. So this is actually the quantity of goods that are demanded by consumers like you and I, and this is just the price of the item. So I'm really going to say that revenue R equals price P times quantity Q. Okay, so I'm going to take the derivative of this, and I'm going to look at how revenue changes with respect to price. Okay, so I believe in every single example, we've either done ddx or ddt with respect to x and t. But now we're going to take the derivative with respect to price and see what that represents. Okay, so now I'm going to differentiate with respect to price. Okay. Now, one tiny little assumption that we're making right now, and I think it's a valid assumption myself. We're assuming that quantity, or the number of items that are sold, can be figured out from the price of the item. And there are supply and demand curves and a whole microeconomics, if you want to take a class on that, that relates price and quantity. So I think it's a valid assumption, but I do have to write that as an assumption. Okay, so one assumption is that quantity demanded is really a function of price. Right, because we are taking the derivative with respect to price. So if this doesn't have anything to do with price, well then we have a situation that I'm not ready to talk about yet. All right, so how do I take the derivative with respect to price of r? What does that represent? Well, according to Leibniz notation, all you would do is write this as dr dp. The derivative with respect to price of r is really the derivative of r with respect to p. So how is revenue the change in revenue with respect to price? Now let's just think about this for a second before I use the product rule. If I increase the price of a good or service, I'm expected to make more money, right? If I increase how much something costs, I'm taking home more money to an extent. Eventually, consumers are going to stop buying my goods. So we're going to look at where that levels off. All right, so like I said, the reason we're going to use the product rule, well, we have two functions. We have two functions of price being multiplied together. Two functions of this variable. Okay, so here I'm going to use product rule. And if you will recall what the product rule says you take the first function times the derivative of the second plus the second times the derivative of the first, which is price. Okay, so let's actually evaluate this. The derivative with respect to price of Q. We have a similar notation when we took the derivative with respect to price of R. So what this ends up being is P times this quantity. Well, ddp of Q is really dq dp. I'll explain that in a minute. Plus Q times, what's the derivative with respect to x of a function x? If these variables match up and it's a single variable, this evaluates to 1. It's really Q times 1, which is just Q. So we get this expression. So here's what it says. Here is how revenue changes with price. It depends on the quantity. More quantity of goods sold, more your revenue changes. But it also depends on price to an extent. It depends on it depending on this dq dp. Well, think really hard about what happens when I increase my price. If I increase my price, less people are going to buy it. So the rate of change of quantity with respect to price is actually probably almost always going to be a negative number. But there's a difference between negative 0.005 and negative 20, right? There's a huge difference. So depending on how small this is or how close this is to 0, it's going to depend on quantity. That's something to think about, right? Now, I'm about to teach you how to differentiate any elementary function, any function that any teacher gives you ever. I'm going to teach you how to do it right now. And your question is, well, didn't I already learn how to do that? Didn't you show us some properties? I did, but those were only assuming that whatever was inside of your function, like sine or exponential, was a single variable x. Okay, so given a function f of x, if I differentiate it, I am assuming that the inside of that function, the argument, if you will, is a single x. So it has to be a single x. So if I gave you a question like, if I wanted you to find the derivative of, say, sine of 2x, you wouldn't be able to do that right now. This has to be an x for you to use that definition. The derivative of sine of x is cosine of x. What's the derivative of sine of 2x? That's a mystery right now. Okay. Same thing goes if I wanted to take the derivative of, say, e to the pi x. Pi is 3.14. Right? don't know how to do that. Or if I wanted to take the derivative of, say, the square root of x plus 1. I know how to take the derivative of the square root of x because I could raise the square root of x as x to the 1/2 power. But I don't know how to raise this entire thing to the 1/2 power and differentiate because this isn't x. So I run into a small problem. Okay, so I want to know how to differentiate with an argument that is not x. Okay, I'm going to approach this graphically to start out with. So I am going to look at sine of x and compare those functions to see what we're looking at, right? So if I have three scenarios, three graphs, okay, we'll start with the basic sine of x. So if I graph y equals sine of x, I'm going to get something that looks like this, give or take. Okay, so if I wanted to differentiate that, you know the derivative is cosine of x. So dy dx, how this function is changing depends on the function cosine of x. Now I'm going to introduce a new function. We're going to say, well, I don't know, to label it something different. I'll just say y, doesn't really matter. Y equals sine of 2x. Okay, so this 2x means that I am periodically changing. I am oscillating this function at twice the rate. So in this horizontal distance, I actually go up and down twice. I go around the unit circle 2 times. Okay, so it's going to look something like that. And if I had something like y equals sine of 1/2 x, I complete one trip around the unit circle in half the time, I guess. Okay, or another way of thinking about it is it takes twice the distance to complete one cycle. Okay, so it really looks something like that. And if I asked you what the derivatives of these functions were, well, this one you could actually probably figure out with analytic methods from what you know right now. Because sine of 2x is a trig identity. You can split that into, if you really wanted to, you can call this 2 times sine of x times cosine of x. And you could use the product rule. In fact, you already kind of know what's going to happen, because if I rewrite sine of 2x as 2 times sine of x cosine of x, I had to pull this factor of 2 out. So it's 2 times whatever this product rule ends up being. Well, isn't that what I would expect anyway? A 2 out in front? Because if this happens at twice the rate, I'm squeezing this function in to half the space. So if I had some sort of a tangent line right here, if it changes at cosine of x, this is expected to change at twice the rate. Okay, instead of traveling like this, it's going to be smushed up, right? So you'd expect this to increase at a rate of 2 compared to this function. Likewise here, you're stretching out the function. So you'd expect this derivative to essentially be cut in half by a factor of 1/2, because it takes more time, so the slopes are going to be more distinguished. Okay, so that's kind of the general principle behind the chain rule, which I'm going to go and define. So the most important rule, I think, in all of differential calculus is the chain rule. So I'm going to define it, then we're going to go through a proof. So here's what the chain rule says. Suppose a function has an argument other than x, like we've been doing. Okay. So here's what the derivative is. So I guess I'll do it in red because it's so important. The derivative with respect to x of what's called a composite function. So instead of an argument of x, it's going to be something else. It's going to be another function of x. Okay, so in this case, the function is 2x. In this case, it's 1/2 x. In this example, the function here is pi x. I could have another example with a ddx of, be really crazy, I could do the natural log of, well, I don't know, the sine of x. In which case, the natural log is my function, but it has another function as an argument. Okay, so you're going to see a lot of those. So if I have another function inside of a function, it's called a composite. This is equal to the following. It's equal to f prime of g of x times g prime of x. That is the chain rule. Box that, highlight it, do whatever you want, memorize this rule because it is one of the most important in all of differential calculus. I said that before. Okay, so this derivative has two components. Just like these derivatives, we kind of thought of them as having two components, right? So on the first component, the derivative of sine of x is always just going to be cosine of x. So maybe you'd think the derivative of sine of 2x would be cosine of 2x, right? Because the outside function is sine of x. That's what I'm doing overall. I'm taking the sine of something. The derivative of that is cosine of something. Okay, and then you have this other component where the argument is 2x instead of x. So you multiply it by an extra factor. So the chain rule ends up being kind of like peeling off layers of an onion. Meaning you have an outside function and you have an inside function. And to get the derivative of the composite function, you multiply both of those together. So you should always have at least two components right here. Right? So I want to go through a very simple proof, and there are several proofs of this online, but I like one of them using Leibniz notation. Okay, so I believe Leibniz actually discovered the proof first. He made like a sign error, but I'm not going to judge him too harshly for that, of course. So we're going to do this. Let's suppose that I have a function. I have a function f, and I'm differentiating that function. So I want to find df, the derivative of f, with respect to x. Okay. Well, we realized that this is the same thing as the derivative with respect to x of this composite function of f of g of x. Okay, now what I'm going to do is I'm going to let this inner function g of x just equal another variable u. Right now, instead of differentiating with respect to x, instead of doing that, I'm going to differentiate with respect to u. You're going to see why that makes sense in just a minute. So we're going to differentiate this function with respect to u. Right? So instead of g of x, I'm going to replace it with a u, and instead of d dx, I'm going to find d du. So what this is going to end up equaling is my df dx. It's really going to be, well, I'm going to change this. Instead of d dx, I'm going to say it's d du of f of u. Right? So after I differentiate this function, it's a function in terms of u. I plug u into the function, and what I end up getting is the derivative with respect to u. Okay, but there's a catch now. My function is now in terms of u. So another way of saying that is after I complete this, I'm taking the derivative of a function f, but now what I have this is actually df du. I'm taking the derivative of my function f with respect to this variable u. Well, I don't want that. I want to take the derivative with respect to x. Is there a way I can do that? Yes. I said there are two components to the chain rule. There's this initial component, and then you multiply it by something. Well, I don't want this du anymore. I want to get rid of it. Okay, so since this is on the denominator, if I put this on the numerator, these will cancel out. But since I want it to be in terms of x, I'm also going to put a dx on the denominator. All right? So in actuality, if I multiply by this, whatever this is, du dx, hopefully it should make sense that these du's are going to cancel, and I get exactly what I wanted. I got df dx. So we're letting g of x, this complex function inside a function, we're letting it equal u, and we're differentiating with respect to u. So this is giving us the derivative of the function with respect to u. Now I'm saying in addition, we have to multiply this function by du dx. What is du dx? Well, remember in the very beginning when we let g of x equal u, so all I need to do is find du dx. Well, it turns out that if u equals g of x, and I want to differentiate this function with respect to x now, I really do exactly what I did in the beginning. Take the derivative with respect to x, and I figure out what that's going to be. So on the left-hand side, Leibniz notation tells us this is du dx. Oh hey, exactly what we wanted. And on the right-hand side, I have the derivative with respect to x of g of x. That's just g prime of x. So with this in mind, I'm multiplying whatever this is by g prime of x. Right? So let me just do a 20-second recap before I write my final statement here. So I wanted to prove the derivative of a function with respect to x of some composite function, where I have an outside function, but the inside function isn't x, it's some variation of x squared, sine of x, whatever. It's more complicated than just a single x. So in order to differentiate that, I'm simplifying the process by letting this equal u. Okay, and I'm differentiating with respect to u. But by differentiating with respect to u, I have the quantity df du. So instead of df du, I want df dx. So to get from here to here, I have to multiply by this extra factor so that these du's go away. So we found df du to be equal to this quantity. Okay? Or another way of stating that is df du is really equal to the derivative of this function. I'm not worrying about what's on the inside. I don't care. I'm just differentiating the outside function f, and I'm leaving the inside alone. But I have to multiply by this extra factor to get df dx. I have to multiply by this du dx. But we figured, well, if I just let u equal g of x, like we did for our initial substitution, if I differentiate both sides with respect to x, we end up getting that du dx is equal to g prime of x. So since du dx is g prime of x, I need to multiply both of these together to get my overall derivative. So I'm going to write it one more time in red, just to emphasize it, that df dx is f prime of whatever g of x is equal to times g prime of x, where this is my outside function and this is my inside function. I'm even going to box it. So I'm going to work a few examples just to make sure we're on the same page with the chain rule. Okay. So my first example, if I can't complicate things enough, is we're going to differentiate sine of tangent of x. Okay, please don't freak out. It's going to be fine. Because in reality, all this is sine of something. I'm differentiating sine of something. Well, that's just cosine of something. It's as simple as that. But for the first few, I'm going to show all my steps. I'm going to show the chain rule in action. But eventually you're going to get to a point where you can just write outside function times inside function. Write it as an answer. Just like those practices with limits and derivatives, you should be getting quasi-comfortable with it right now. Okay, so the first thing I'm going to do is I'm going to let my inside function equal u and differentiate with respect to u. So suppose u equals tangent of x. Okay. Now, I know I'm going to need it later, but if I take the derivative of the inside function with respect to x, du dx ends up being, well, what's the derivative of tangent of x? Well, we know that's actually secant squared of x. Okay. So, in order to find dy dx, first I'm differentiating with respect to u. So I'm taking d du, and this variable could be anything, by the way, but I picked u. It's arbitrary. So I'm taking the derivative with respect to u of sine of u. So that's my outside function. But now I'm in terms of u. To get in terms of x, I have to multiply by this additional factor. So I have to multiply by du dx. So again, if you want to be sneaky, you can actually take these fractions and say, well, actually, these du's are going to cancel out, and I'm taking d dx, which is what we want. That's what you're actually doing. But we have to do it in this process to make sure we're getting both the outside and the inside function. So the derivative with respect to u of sine of u, that's just cosine of u. So this equals, well, this part is cosine of u, the outside function. And this function right here, well, we found that if I differentiate the inside function with respect to x, we get secant squared of x. So this is actually secant squared of x. All right, and the last thing I'm going to do is to make sure everything is in terms of the variable I want. Okay, so I'm differentiating y, but I want it all to be with respect to x. So instead of cosine of u, I'm going to make a substitution and say this is actually cosine of u equals tangent of x. This is really tangent of x times secant squared of x. Okay. That's my answer. All right, let's do another example. So suppose I make things a little harder, like they weren't already. I want to differentiate the natural log of the square root of e to the x squared minus the square root of 10. Okay, before you exit out, it's fine, don't worry about it. Please just stick with me. I promise it'll get better. I'm showing you the hard examples so that you'll get to class, you'll get to exams, and you'll be like, oh, it's actually much easier than it was on here. All right, so the natural log of, and then a bunch of crap. I don't care about that crap, but the first thing I am going to say is, well, if you notice, make life easier on yourself when you can. Okay, so I always tell people, avoid the quotient rule when you can. Another little trick that you can use, I'm taking the natural log of the square root of something. Well, if I took the natural log of, say, x to the 5th power, so just as an example, if I took the natural log of x to some power, according to some really cool properties of logarithms, I can move this out in front as a coefficient. So this is really 5 times the natural log of x. How can I apply that here? Well, this square root function is really saying I'm raising whatever this crap is to the 1/2 power. So this is to the 1/2 power. I can move that 1/2 in front as a coefficient and make my life so much easier. All right, so I'm going to do that. So just doing algebra right now, no derivatives, but if I wanted to find dy dx, so dy dx would be 1/2 times the derivative with respect to x of, well, now I just have the natural log of e to the x squared minus the square root of 10. So that looks a little better, right? So I'm not necessarily going to show the steps that I did before, but I will say that, like the chain rule, there's always going to be an outside and an inside component. What are you actually taking the derivative of? Well, I'm taking the derivative of the natural log of something. Well, you know that the derivative of the natural log of x is 1 over x. So if I'm taking the derivative of the natural log of complicated stuff, that's going to equal this 1/2 right here. That is going to equal 1 divided by complicated stuff, e to the x squared minus the square root of 10. So this right here would be my outside function. Okay, but you know in actuality you're really setting this to equal some variable u and differentiating with respect to u. But since I'm in terms of that variable u, I have to multiply by whatever this derivative is with respect to x. So I now have to differentiate and take the derivative with respect to x of this inside function. My inside function is e to the x squared minus the square root of 10. Well, I run into another problem. I run into another application of the chain rule, because I'm taking the derivative of e to something that isn't x. It's x squared. So here I have another outside function. Okay, so my outside function ends up being, well, the derivative of e to the x is e to the x. So you would expect the derivative of e to the x squared to just be e to the x squared. So this ends up being e to the x squared times the inside function. Well, the inside function is x squared, and if I differentiate that with respect to x, so this is my inside function, derivative with respect to x of my inside function ends up being 2 times x. Okay, so this is my inside function. All this is work I'm doing for my inside function. Right? So I end up getting that this is equal to 2x, right, using a power rule, times e to the x squared. So a 20-second recap, I'm taking the derivative of this natural log. It looks really complicated. The first thing I can do to help the situation is by taking this e to the x squared minus the square root of 10, that's under the square root. Well, if it's under the square root, it's actually being raised to the 1/2 power. So if it's raised to the 1/2 power, a property of logarithms tells me I can move that 1/2 out as a coefficient. So I did that. Here's my 1/2. Now I'm taking the derivative of this complicated expression, but it's just a natural log. And we know that the derivative of any natural log is 1 over whatever this is. So it's 1 over this quantity. And that's my outside, that's my overarching derivative, what I'm doing. But I have to multiply that by whatever the derivative of the inside function is. Well, the derivative of this inside function, you could break it up into term by term. The derivative of this, it's a constant, it's an irrational number, but it's still a number, goes to 0. So I'm only left with the derivative of this. Well, that's going to require another use of the chain rule. So if I differentiate this, I look at the overarching function and I realize I'm differentiating e to something. Well, it's just e to that something. But I have to multiply by the inside function, which is x squared. The derivative of x squared is 2x. So the inside function, this guy right here, ignoring the natural log, is 2x, the inside function, times e to the x squared, the outside function. So if I take the outside function times the inside function, I get dy dx. So dy dx is really, well, it's really 1 over e to the x squared minus the square root of 10 times the inside function, 2x e to the x squared. Okay, so finally I realized that these 2's, that the 2 and the 1/2 cancel, right? Those cancel nicely. And I'm left with the final answer of, squeeze it in here, x times e to the x squared divided by e to the x squared minus the square root of 10. Please don't judge me for cramming that into a small space, but that is the answer. Right. All right. Now, before I scared almost all of you away, the people that are remaining, I want to look at some really cool applications of the chain rule really quickly. So, one of the first applications I want to look at, well, we can now take the derivative of basically anything that we want, which is really cool. So, let's take the derivative of a circle. So I want to find the derivative. Of a circle. We'll center at the origin to make it easier. Alright, so you should know that a circle is defined by two things. It's defined by its center, and it's defined by its radius. So we'll say the center, the origin, 0, 0. And oh, I don't know, let's be whimsical and say the radius is a. Let's be scandalous instead of r, because I feel like r is way too often used. So we're going to use a because I said so. And this radius right here meets at the point a comma 0. And this radius at this point meets at 0 comma a. Alright, that's enough black. Alright. So the equation of a circle, in general, is given by the expression x squared plus y squared equals the radius squared. Okay, and these would be different. These would be x minus whatever the x coordinate of your center is, y minus whatever the y coordinate of your center is, but in both cases it's 0 and it doesn't matter. They cancel out to be x squared plus y squared equals a squared. Okay, please review conic sections if you don't know that. Now I want to differentiate this. Well, I can't differentiate this right now because I don't have y as a function of x. So you have to algebraically manipulate this. Okay, so if I wanted to do that, I would subtract x squared from both sides. I'd get y squared equals a constant a squared minus x squared. And then lastly, I take the square root of both sides. But you should remember that if I take the square root of both sides in an equation, you have to introduce plus and minus. Okay, so the square root and the squared cancel, but I have to put a plus and minus, and here's why. So right now I have y equals the square root of a squared minus x squared. Since this is a circle, all around this circle it is symmetric about this point, the origin. Meaning it can have both negative components and positive components, or a mixture of both. Right now, as I have y as a function of x, y can only be positive. Because technically, a square root, unless you want to talk imaginary numbers, which we do not, this class is pretty much all real numbers, this has to be a positive number, whatever it is. Okay, so in order to introduce the fact that we can have both positive and negative components, we do have to put a plus and minus right here. Because without the plus and minus, we're only talking about the upper portion, talking about this semicircle. So to get the full circle, you have to put plus and minus. All right, so I want to take the derivative of this expression. Well, if I want to differentiate with respect to x, what I have is an application of the chain rule. Yay! So dy dx ends up being the derivative with respect to x of the square root of something. Well, I'm just going to tell you the derivative of the square root of x is 1 over 2 times the square root of x. So I'm going to replace x with that junk. Right, and that's because if y equaled the square root of x, dy dx equals 1 over 2 times the square root of x. You can verify that if you want, but hopefully you're sensing a pattern here. It's the same thing, 1 over 2 times the square root of, but instead of x we have a squared minus x squared, so I just put that right there. But we have to multiply it by the derivative of the inside function. So what is that going to be? Well, this is a constant, so this, so our big function, our outside function, that's what this was. And our inside function, this guy, the derivative of a constant is 0, and the derivative of a negative x squared, if I bring this 2 down, it's negative 2x. Right? So finally, the 2's cancel. Okay, and I'm left with dy dx equaling negative x over the quantity square root of a squared minus x squared. And if you're wondering where my plus and minus went, technically with this square root component alone, this component can never be negative, so that can never be negative. So we have to put plus and minus. But here, since I have an x, well, x can be positive or negative, so the numerator can be positive or negative, which means this entire expression can be positive or negative, so it evens out. Right? Right, so I realized this was kind of a short lecture, but I did go over a lot of stuff. In the next video, we're actually going to pick up right on finding the derivative of this function in a much simpler manner. So we're going to talk implicit differentiation. I have some inverse functions for us, and we're going to have a blast. So thank you again for being so attentive, and I appreciate it.